first of all, Mark's just done a fantastic job of introducing me there. But now my name is Freya, or Frey. You can get me on Twitter here, although I don't tweet very often, but I keep trying to tweet more, and I'll go through fits and starts of it, so feel free. I'm currently a penetration tester for Sec1, or Clarinet, as we're now part of as well. They let me come here on the proviso that I made my slides look nice and red, and also that I say we're hiring. So if you're interested, come and let me know. I actually did most of this stuff when I was at Leeds University. So I did a physics degree, and then I stayed around and didn't get a job for a while longer and did a PhD, and that was in this sort of stuff. From that, I kind of did a sidetrack. I worked for Huawei for a while doing security research there, and then I came back up to Leeds to do pen testing at Sec1. So if you've got questions about any of those things, feel free to ask me at the end. So I do have the University of Leeds logo there very briefly, so that, and also EPSRC, I should probably credit them slightly because they funded my PhD. But that's why the slides are all red. Okay, so I did a lot of stuff in quantum physics, and I find it really hard to understand. Like, we were talking about this in the break, like there are bits of quantum physics where I'll read it and I'll understand it and I'll stay in my brain for about an hour, maybe 2 hours, something like that. And then it slowly kind of exponentially leaves my brain and I have no idea what it is anymore. And then I have to read it all over again. So actually this is quite frustrating when you're doing a PhD, when you have to keep rereading and like reassuring yourself that you are doing the right thing and you haven't gone crazy in between. Maybe I did go crazy in between. That also could be a valid thing. But it's really, really tough stuff, whether or not you've been doing it for a term at degree level or for 4 or 5 years for a PhD and beyond as well. So, what even is quantum anyway? What does quantum actually mean? So, the best way to describe it is we'll start with what the word quantum itself actually means. And quantum just means the smallest possible finite amount of stuff. Okay, so a quantum is a smallest possible finite amount of something, blob of whatever it is. So a quantum of beans is the smallest possible finite amount of beans you could have. Okay, and the word quantum gets used really, really badly, and it makes me really mad. And actually some of my friends send me pictures of this sort of thing all the time because they know how wound up I get about it. If you come across any at the end of this talk, feel free to tweet them to me. I'm debating making a Twitter account dedicated to just bad quantum. So yeah, a few examples here. So this is the smallest possible finite amount of pan. If you can't see it, it's written there. Don't really know what that means. The smallest possible finite amount of dry. If any of you use Shore, you might, want to be aware that evidently then it's not that dry. It's not making it that dry. It's the smallest possible finite amount of dry. I don't even know what this means. Not really sure there. This one is someone sent me, the smallest possible amount of soft toilet roll. This is my personal favourite because I think they're probably actually right. Scientists make the smallest possible leap towards a secure kind of internet. So, actually, this is all essentially rubbish. People have taken this word and they've got excited about it and they like to put it in front of things because they think it makes them sound clever or their product sound shiny and new and in some way of some kind of technology involved that actually isn't all that relevant. What does that actually mean in the context of physics? So we'll start with what things normally are. So classical is what we call it, when things are completely normal. And we're talking here like if I hit this table, I'm expecting this table to stop my hand, unless I, am suddenly super strong and I break it, but I don't want to go around breaking things. I think Mark might kill me. And, classical things, they behave the way we're expecting them to. It's in the macro world, like we're talking about things as big things, tangible. We can see them, we can touch them, we can feel them. And then when you take that down a little bit and start to see what actually makes up this stuff, what is this table made of, when we take it right down to the smallest possible finite blocks of matter we can, things start to act really weirdly, and they start to do crazy things, and we don't really know why they do the things that they do, but they do. And if you put lots of them together, then they create this macro effect that's classical, and we can understand it quite well. Newton was very good at it. He gave us lots of equations and things like that. But so when we're looking really at the small stuff, it goes a bit weird. And so quantum in the physics sense just means we're looking at the smallest possible finite amounts of matter. And there is a limit to the smallest possible amount of matter that we can have as well, based on how much energy it's got and that kind of thing. So we can sometimes try and use the really weird things that stuff does when it's really small to our advantage. And at that point, we might start developing new technology. So there are certain kinds of particle that are, smallest finite amounts of particles that do kind of weird things, and we can use that in coatings for stuff like that. For example, silver particles, they have certain antiseptic properties, and at that point, it's a quantum technology. It's based on the quantum effects, and we can do the same thing with computing and with cryptography as well. So, talking about that a little bit more, I should say here that there is very little maths involved. So hopefully you don't need a degree in maths or physics to actually follow what I'm saying. But if anyone does get a little bit lost, feel free to shout out, because I can't remember what it was like. So just let me know. If we imagine that we've just got some water, say, and we send it through two slits, we would expect the waves that water has. So we're assuming this is maybe like the sea or something like that. And there's a wall and there's two holes in that wall, and the waves would go through, but they would do something a little bit weird, like bits where the waves crash together, they would make a big wave. And if you had the dip down part of a wave and the high up part of a wave meet at the same time, that would just disappear to nothing. And you would get a sort of pattern like this. So the white bits are where the waves have come together and made a big one, and the dark bits are where kind of the down part of the wave and the up part of the wave have come together to give you nothing at all. This is called an interference pattern, and this is kind of what we'd expect if we were to look at something like water in a classical sense. And if we were to take a load of tennis balls, and we were to throw them through the same slits, the same holes in that wall, we would expect it to hit the wall at the 2 points where the holes are, right? So tennis balls are kind of like particles, and you're throwing them through and they're just hitting the wall, and you're getting these two bits build up where the tennis balls hit. And there might be a little bit of variance in that. It won't be exactly in line with the where the slit is, because some of the tennis balls will probably bounce off a little bit, but it's going to be in these two separate blocks that you see them hit. If you were to do this with light, if you did it one at a time and you measured it in the right place, and especially if you only if you were only looking through one of those holes and you blocked the other one off and you were just firing your light through that one hole, you would get this kind of thing. You might get something else in there called a diffraction pattern, but we won't worry too much about that. What we're saying is you'd get this one big blob. But if you took that, if you opened up that second hole in the wall, you'd start to get the same thing that you see when you see waves. So you're you've still got these things where if you're sending individual tiny bits of light called photons, so photons are the smallest possible finite amount of light, you would still see the individual blobs hitting the screen, but it's in the same sort of pattern that you'd see if you have waves. So it's kind of got this weird nature where it's doing something that's a little bit of both, and we don't really understand why. We can describe it quite well with equations and maths. So you may or may not have heard of the Schrödinger equation and things like that. We can talk about it quite well, and we can predict it based off that as well, because we have these really good mathematical models that say we can predict if we cover one slit, then yes, it would only give us, one blob, and whatever. If we opened it up, then we'd get this interference pattern. We can describe it. Doesn't mean we actually have a clue why that's happening. So yeah, if you do it with light, and it's going through both, you can see how it's kind of going out here into that kind of pattern. And this is actually from some real experiments that have been done. And you can see that you've got starting to build up here. So at the A there, or actually it's labeled B, that one is where, there's only a couple that have been sent through, but as you send more and more through, you start to see this pattern that's like this interference pattern, but each of the individual white dots on there is a separate individual photon. And it's kind of interesting because, you can see here, this is kind of describing both of them. So you're sending your individual source of particles through, and if you were to hold your telescope or your detector over one of the slits and it was quite close, you would see kind of this sort of thing. So if we cover that one over and just measured it here, we'd see this, and vice versa if we just look at the bottom one. But if we open them both up, we can see kind of this full pattern. And interestingly, if you just take the photons one at a time, and you don't fire lots of them all at once, and you just fire it, and then you wait a little bit, and then you fire another one, and you can set some kind of trigger here to detect whether or not it's gone through the left side or the right side, and you would see that it's gone through only one of them. But if you waited long enough and you did enough, you'd still build up this pattern where it's got all of the different fringes. It's kind of weird, and we can use this to our advantage in quantum computing and that sort of thing. So I'm going to sort of build up a concept here where if we're looking at all of the ones that just went through one of the slits, we're going to call that S1 or 1. And if we look at all of the ones that go through the other slit, we're going to call that S2. But if we look at the combination of them, we can combine those together and say that they are, I'm trying to think of the right word, like entangled in some way. So here we've got this is what we'd call them. So this is the ones that have gone through the first slit. We call them 0 in this instance, and we put the funny little brackets around them just to define that they're quantum. And if we look at those specifically, that's, it's just going through one of the slits, and we can imagine that those are the ones that are kind of having this kind of effect. And if we look at the ones that have combined, and we've added them both together, they're the ones that are kind of having this sort of effect. So when you look at it and you're seeing this, and you're looking at it from that perspective, it's this sort of description that we're looking at. And when we're looking at them through the perspective of it just being discrete separate lumps, that's when you've just got the 0 and you've just got the 1. And that's kind of a little bit like bits. So, you're nearly all computery type people. You have a 0 and a 1 bit. And we have the same thing. We have a 0 bit and a 1 bit. We've just put funny brackets around them because we're using quantum physics. And then we have this other concept as well where we've added them together, and we can call that a qubit as well. So if you're using quantum physics in this way, we call them qubits. So I'm going to talk a little bit about what quantum computing actually is and what sorts of things we can do with it. Anne's going to talk a little bit later about how good it is or it isn't and what sorts of things are out there. So you've got that to look forward to with Anne. So we've talked about how we've got stuff going through one slit and we can call that 0. And if we wanted to, we could describe any particle, any photon, as having some properties that you could look at it from the perspective of it's got a 0 or a 1. And here we can say it's pointing up or it's pointing down. Or we can look at it from the perspective of it actually being a little bit in all of the different places. It just has a probability that it's going to look in that interference pattern. And we can kind of describe that by this funny symbol here. That it's dying slightly. So the funny symbol there, that's just that 0 plus 1 stuff that we were looking at in a certain combination. And we can use these qubits to build up gates as well. So you are probably all familiar with the concept of a NOT gate, where you take a bit and if it's a 0, you turn it into a 1. If it's a 1, you turn it into a 0. And gates are essentially ways to manipulate bits. In the same way, quantum gates can manipulate quantum bits as well. So we can have the same thing where we transform our photon, we can do some stuff on it, we can put some actions on it and move it around and make that that movement into a gate as well. So, for example, the Pauli gate takes something that's pointing in that direction as a 0 and make it point in the other direction as a 1. Yeah.
Is that named after, as in exclusion? Is it exclusion principle?
The uncertainty principle. Yes. Yeah. Same person, Pauli.
Yeah. What does the gate do on non-integer values for the rate?
That is quite a good question. It's quite a complicated one. Do you go into that at all in your talk? No, you don't? Okay. It's essentially a matrix transformation. If you've got non-integer values, or you've got a combination of the two, they're going to have different values at different points in the matrix, and the Pauli gate will transform that matrix into something else in a sort of slightly more complex way. We can talk it a little bit more at the end if you want. Yeah, cool, awesome. So as well as that X gate, that NOT gate, we have these others, and they don't really translate into the same kind of like AND gates or OR gates that we have in like classical computing. But they can do slightly weird things, and we can do something called the Hadamard gate, which is where we look at it from a completely different perspective, and we take two and we can combine them. You can build these up to make different circuits. And different circuits can do different kinds of things, different kinds of algorithms. Anne, I think, is going to talk a little bit about the different sorts of algorithms you can have. And I'm going to quickly sort of talk about, we've got this, which is great, but it doesn't mean that we can make computers really, really, really fast. It doesn't mean that you can open Microsoft Word in a blink of a second and it doesn't take forever to load anything. That isn't what quantum computing does. And it's quite a common misconception, is that quantum computers, that means we can do stuff really fast. It means that we can do some things really fast because we're doing them in a different way, but it doesn't mean that we're just going to make computers better in general. And it is because we've got these different kinds of algorithms where we're building up these gates in different ways. And those of you who are familiar with like complexity theory and stuff like that, you have, I don't know, a mathematical problem that is really easy to solve with classical thinking and classical computers. And you have ones that are really hard to solve with classical computers, and we don't know how to do them. So factoring prime numbers is a common one that you might have heard of before. But these new algorithms can potentially make those work really, really well. We can calculate prime factors really, really quite quickly using a special kind of algorithm. It's called Shor's algorithm. And it kind of, some of them will overlap with classical ways of doing things at the minute, and some of them are just completely new. And there are a whole load of algorithms out there that haven't been invented yet. Like, we're quite early stages here. There's maybe about Shor's, Grover's, the ones I can think of off the top of my head, and a couple more. But there are a whole load of problems out there waiting to be solved that people just haven't looked at yet. Yes.
I know we still haven't worked out whether some problems are harder than others, the P equals NP.
Mm-hmm.
Has it been proven that quantum computers can solve some problems faster than classical Turing machines, or is that up for debate?
So something like Shor's algorithm does solve the prime factor problem quicker in terms of the number of steps that it takes. It has some classical steps in there as well. And then there's one quantum bit that basically just makes it you solve it in fewer steps. And that has been proven. Whether or not it takes less time, it depends on how good
I meant like the complexity is. Because if you could show that computers could do that, because I assume it's polynomial time, so they're on. If you show that was significantly faster than a classical Turing machine, you sort of start solving bits of time complexity.
Yes, essentially. So I'm not a massive expert in complexity and things like that, but I'm fairly certain that like the quantum algorithms have been proven to solve in far fewer steps than like the classical solutions to them as well, which is why people really care about this sort of stuff, because if we can make it work, then we solve a whole load of issues that people have been worried about for a while, like how can we actually solve these problems. And it's only like certain problems that we've kind of thought about the answers to. So protein folding is a really interesting one that is really, really, really hard. We can only model like a couple of proteins, like quite small ones. But there's potentially quantum algorithms out there that are dramatically better for that. You look like you had something to add to that. No? Okay.
Does this Shor's algorithm actually, factoring prime numbers, does this actually translate into possibly breaking the then?
Yes, it does. And in fact, that's very much kind of the next bit where I'm going to go with this. There was someone else with their hand up over there, so
I
just want to...
I just wanted to... Can you quickly clarify what your complexity class Q is supposed to be? Is it polynomial time solvable with the quantum, or yeah? What's your?
In this instance, I'm just using it to vaguely mean like solvable within like the time of the universe. So like it really depends on the problem that you're looking at.
Intractable.
Yes. So complexity in the time that is, not necessarily polynomial or not, but just better than the current version, better than like polynomial or whatever it is that we've got at the minute. Okay, so talking a little bit about how good quantum computing is or isn't. I'm kind of going to defer this to Anne later. But some of you may have read the press release from Google, or rather the leaks about Google and their potential quantum computer that they've got. Okay, so exactly what you were saying. So Shor's algorithm, this is a way that we can factorize prime numbers potentially quite quickly. And that does have applications for, people in this room. You'd probably deal with crypto at various points in various levels, depending on what it is that you do. At the minute, we've got a AES-256, we've got Diffie Hellman key exchange, things like that. These kind of rely on concepts such as the fact that prime numbers, or in fact the big numbers, are really, really, really hard to factorize into their individual prime factors. That is a really tough problem that computers can't solve within, before the heat death of the universe. Whereas with a quantum computer, we can do it fairly quickly, potentially, depending on how good your computer is. So this is where it starts kind of getting interesting a little bit. And just in a sort of a bit of a noddy way here, so the idea of how cryptography kind of works is you have your secret, you put a lock on it, you pass it over to your other person, they put a lock on it, you bring it back to yourself, you take off the lock that you've got, and you give it back to Bob, and then they can take their lock off because they've got the key for their padlocks. And that way you've never left this secret unlocked at any point, and we've managed to, transfer this over. And you can describe the same sort of concept with kind of colours. So the idea that you've got a common thing, and then so that could be like your public key, and then you add your sort of private bit to it. You can shake it up, mix it together, and it's got to be really hard to unmix that. And then you can swap them over, and you can add your own colours to it again, and then you both end up with something that looks the same. But at no point have you revealed what your secret colour is. You just know that it looks the same at the end. And the thing about that is the lock in between, or that bit where separating the colours is really, really difficult. At the minute, that's based on this thing of prime factors being really, really hard. So that mixture separation difficulty is, it is really, really difficult to take this really big number and know what the prime number I started with was and the prime number that the other person started with was, and go from there. So obviously that's great as it is, but if you've got a quantum computer and it works really, really well, then you can break that and you can figure out what people's private keys are and that sort of thing. If you really care about this sort of thing, I don't know, maybe you're a bank or you're a nation state, or you're just really ahead of the curve and you're really nervous about when the quantum revolution is coming, you've got a couple of different options you can think of. You can think about a quantum solution. So this is a problem that's been brought about by quantum existing, and we can think of a quantum solution to this. So we can, again, use the weirdness of physics to try and come up with an answer. Can we use the weirdness of physics to do cryptography? So there's another weird concept. It's called entanglement, where basically if I take two quantum particles and I mix them together in a certain way, I can entangle them so that when you do something to one of them, the same thing happens to that other particle. And I could mix some entangled particles. I could keep one. I could give my other one to Anne. And, I could rotate that particle around. She would see hers rotating. And through that, we could transmit a message. And there is nothing, I can't put anything in the middle. I can't do anything else to it. Someone might be able to measure what's going on, but then the whole thing would deteriorate, and we would know, so it wouldn't work. But in that sense, that is one way that we could use quantum physics to find a solution to this. Or we could think about doing it in other ways. I don't know, can we find an inherent property of mathematics? Or can we just use classical ways of thinking or out-of-the-box ways of thinking to try and defeat this problem, rather than coming up with an ever more complicated solution to what is already quite a confusing problem. And a lot of people really care about doing it the complicated way. they like to sort of make things as hard as they possibly can for themselves and for everybody else. And I don't know why they do this, but they do it. And it's because it's interesting stuff, right? Like, quantum physics is really fascinating, and it would be really cool if you could come up with an answer that used all this really fascinating stuff, but it doesn't necessarily have to be. All we really want is something that can be transportable. We can use it in a lot of different situations. Ideally, we could just integrate it with computers as they are now, rather than having to put in some kind of crazy quantum chip box that has particles and lasers and stuff flying around in it, because that's going to look really weird and be really hard to integrate. And because these algorithms are always evolving, we don't really want it to be relying on the idea of stuff that is really hard to solve for a computer, because we have no idea what someone's going to wake up with tomorrow and go, oh, I've got this algorithm that'll solve this computationally difficult problem. So we want to try and find something else that is, separate from this kind of idea as our new way of doing crypto. Maybe the answer to that is using randomness somehow. So randomness is everywhere. It's readily available. It's, all over the place. It's completely inherent. It's built into the universe as it is now. It's inherent even within quantum physics itself. Things are, will not necessarily predictably appear where you want them to be. It will be random. And it doesn't rely on any complex problem solving or anything like that. It doesn't rely on, it is really hard to factorize numbers or anything like that. It's really hard to sort this, or it's really hard to separate these colors. It doesn't rely on any of that. So how could that work? So, okay, I've got a coin, and I'm going to give Mark another coin. You go, catch it. Fab. Okay, right. I'm going to flip my coin several times, and I'm going to get a series of heads and tails at the top, and Mark's going to do the same thing with his, and he's going to get the second row of heads and tails here. I'm just going to move my mouse out of the way. There we go. Every time we match, we could use the times when we match where I get a head and Mark gets a head, or when I get a tail and Mark gets a tail, we can take the bits where they match and use that to create our key, potentially. No one else, if someone else, so I don't know, Anne is wanting to eavesdrop on our conversation, she's got another coin, she's going to match in different places. So if we can find a source of randomness that we can use in this kind of way, maybe we can communicate, we can come up with some system to describe when we've got things that are the same and when we've got things that are different. This is where the only little bit of maths kind of comes into it. And if you want to, you can shut your ears down and I'll give you a wave and let you know when the mathsy bit is finished. But we can use an algorithm. So the algorithm I'm describing here is called advantage distillation. And we can use that to communicate about when our heads are the same, or we both got heads and we both got tails. And the way we can do this is I'm going to do it 4 times, and Mark's going to do his 4 times. And then if I get the same thing 4 times in a row, and Mark gets the same thing 4 times in a row, there's a reasonable chance, or some of the time, they're going to be the same. So I'll have got 4 heads in a row, and Mark will have got 4 heads in a row. I'll have got 4 tails in a row, and Mark will have got 4 tails in a row. And we can write that down, and then we can do some kind of error correction for the times when one of us was wrong, or on the times that was different. All we need is for that to happen not an even number of times, not an equal number of times. So I get matches out of 5 times, I get matches 4 times. And the same goes for Mark. That's all we kind of need, rather than it being we do it 4 times and twice we're right and twice we're wrong. We just need that slight bit of correlation in there. And it's this ever so slightly correlated that we need to be able to take advantage of it in order to do that. And if we had an eavesdropper that's trying to do the same sort of thing, what we need is for her to not be right at the same times that we're right as well. And you might think, oh yeah, but something that's random, it means there's a 50-50% chance of it happening. If we've got a coin and it's going to land on heads 50% of the time and tails 50% of the time, the chances are that we're not going to be right more than half of the times. Except randomness is random too. So that means that it's never going to be 50-50 at any point. It's always going to be 48 and 52 or 49 and 51 or 40 and 60 or something like that. It's always going to be ever so slightly skewed. The amount that it's skewed is going to be random, but it will be skewed one way or the other. And there we go. We've won. We've managed to get that slight weird bit of correlation, and that's all that we kind of need. There are times when Mark will be wrong. Like where I'll be expecting something, and I'll have got a match and Mark will have got a match, but I'll have got heads and Mark will have got tails. And this is where we do our error correction protocols. Maybe it's a turbo coding error correction or something like that. And we can apply that and kind of make it so that we have something that's the majority of the time that's right, or every time he's wrong, we could just get rid of it, ignore that bit, and only use the bits where we know we're right. Yeah, cool. Yeah, life is weird. That's why randomness is random too. We're quite lucky because randomness is everywhere, and this correlation is sort of everywhere as well. Short noise is something that you cannot get away with. Short noise exists in everything. And short noise, if anyone isn't aware, kind of looks a little bit like this. So if you are expecting to measure something at a certain voltage, some of it will be slightly out to one side and some of it will be slightly out to the other side. It's because of quantum physics actually why this actually happens. And we can kind of say every time we measure it slightly to the left, we're going to call that a 0, and every time we measure it slightly to the right, we're going to call that a 1, or a head and a tail, and we can use that to start building up our secret key between each other as well. So this is just essentially every time it lands to the left, we'll call it a head. Every time it lands to the right, we can call it a tail. And we can go through the same process of finding our matches as well. I spent a really long time during my PhD figuring this out, proving that we could do it and whether or not it was true. I did a lot of simulations. I did some experiments as well. Some of them went terribly wrong, but some of them did actually mean that we could create this key and share this key between two people. And that's all well and good. At the minute, though, we don't know necessarily if there's another weird way of thinking about it that means that this is all wrong and we've all been wrong and I've just wasted 5 years of my life thinking about this. But at the minute, I know so far so good, and this is potentially like a viable solution to this. There are other things as well to think about as well. I've just put tapping Faraday cages there, but that's kind of, how secure is us actually receiving this? Can anybody else get in at that point? At the point where I'm receiving it, do I need to be in a completely secure Faraday cage room for this to work and that kind of thing? The question of whether or not this is relevant now, Anne, in very shortly, is going to talk a little bit about where quantum computers are actually at and how good they are. But it's entirely possible that we can use this algorithm in classical computers as they are. Potentially on IoT devices and things like that as well, where actually crypto is really, really hard to do. That's it from me. If you've got any questions, you can potentially ask them now, or I don't know if you want to pass straight to Anne and I'll have a bit of a chat. I don't really mind. Yeah, go for it.
Two things. First of all, how do you mix the results and check them against each other? Because obviously, like a certain vector or something, you have got. How do you do this mixing so that you can do some check afterwards?
So basically, so I would take a completely random number and I would XOR it with my other sets of random numbers. So I'd take the same number 4 times, like a 0 4 times, and I would XOR that with my random stream of heads and tails, and I'd wait for the bits in my series that were the same. So that would mean in my heads and tails, I had 4 heads in a row or 4 tails in a row, as well as like having the bit that I knew about at the beginning.
How do you?
And then, sorry, go on.
Also, how do you authenticate it on the other side? Because you've got some encrypted channel, but you're always inside a man in the middle.
Yeah.
Someone.
So this is a solution that this is a problem that we don't actually have a solution to yet, is there's got to be some pre-authentication that happens. I don't know what the best way to do that authentication would be. Like, how do I know that Mark is Mark? I don't really know, usually because he's loud and scouse, but that is absolutely like a completely valid question, because that's the bit that we don't actually really know the best way to do that yet. Yeah.
What were your thoughts on what we were working on compared to the candidates for quantitative algorithms that sort of get through this there is effort in the community to come up with quantum resistant. So that's
Quantum resistant, yeah. I'll be completely honest, I've not had a massive scrutinization of the candidates that have gone to NIST. I think we were slightly too late to put this to NIST. We thought about it and then the deadline was there. We were like, oh, damn it.
The American government's very keen to get it.
Yes, it absolutely is. Again, personally for me, it kind of comes back to this question of, are you trying to find a really complex solution to something that doesn't actually need to have necessarily a complex solution to? It's got to be something that is distributable, as far as I'm concerned. It's only going to stick if it's easy to spread around. And to be honest, for me personally, that's what my main criteria is. It may well be that there are other solutions in there in the candidates for NIST that are, far better than the one that we've been coming up with, and that's absolutely fantastic if there are. But off the top of my head, I've not been through those submissions completely.
Because you mentioned the possibility of using quantum entanglement as a communication channel.
Yeah.
With the equipment that is required to store the entangled particles.
Yeah.
Is there any reasonable? Is it reasonable to believe that will ever be applicable to household devices, to anything less than mass scale industrial applications?
Yeah.
Within this millennium.
So that is a really, really interesting question. No one really knows. At the minute, we're miles away, to be completely honest. There's so many hurdles we've got to come over. One of them is getting entanglement to last longer than a few minutes. So at the minute, that's currently an issue. Certainly on the scale that we're talking about, we can't get it to last too long before it starts to degrade. And the other thing is that to be able to create these things at the minute, potentially using massive laser chambers, laser tables and ion chambers and things like that. So currently, no. But then if you think about back in like the 50s, a computer took the size of a room, and that's kind of what this sort of thing does at the minute. So potentially at some point, someone will come up with some idea of, I've figured out how we can do this on a chip, which would be, absolutely crazy if it did, but we currently don't have that. And, I don't see any particular candidates on the horizon, but then I don't know all of physics. So. Yeah.
Curiosity with the entanglement thing. It's not something I've heard being discussed necessarily, but do we know exactly why things will entangle and how, over the distance, how they know what happens? Like, how do they happen? How do they change at the same time? And especially when we've got things like Large Hadron Collider looking at Higgs boson, particles that are so difficult to detect, we're now looking to be able to detect them. Mm-hmm. Is there a possibility that that communication is done by some sort of detectable thing that in the future actually it turns out it's just a wiretap on this thing that it becomes tappable, but we just can't see it at the moment?
It comes back to that thing of we can describe quantum physics really well. We have really strong mathematical equations that are very reliable in producing the right sort of answers, but we don't have a clue why it does the thing. Potentially there have been various people that have postulated, yes, there is some sort of carrier particle that goes between, but so far any mathematical reason why that would exist and any physical evidence of that existing hasn't come to fruition.
Wouldn't it also have to be the existence of such a particle would be incompatible with general relativity?
The existence of such a thing is currently not really compatible with any of the mathematical models that we've got to describe quantum physics at the minute. And we don't really know why it does that. It might not be a particle. I don't know. Maybe it's something to do with dark matter or whatever. Like all of these things in physics that we actually have no idea about and are completely unexplored. But we have absolutely no idea. It could be strings vibrating in like string theory or whatever, if depending on whatever it is you subscribe to in your sort of metaphysics and philosophy kind of levels.
The heads and tails thing, it wasn't entirely clear to me where the quantum part fits into that. That
is because it's not a quantum solution. So it's a classical answer using something that's inherent in the properties of the world and the properties of mathematics, rather than it actually being specifically quantum. And that's kind of why this is actually... We're going away from like the idea of something really complex and quantum and entanglement and things like that to the idea of maybe we can just use maths as it is. Yeah. Maybe. I don't know. We could have completely got it wrong, but the quantum kind of comes into it a little bit if you're trying to think how can we extract randomness? So shot noise, for example, that is quantum, and we can use that to give us the randomness. But the concept itself isn't quantum at all, which is why you can see it in there. Yes.
Yeah, thinking more about practical applications, I believe the Chinese recently conducted a demonstration where they transmitted a key from a satellite for a secure video conference. Are you familiar with that? I'm curious if there's any relation to what you presented here and how it differs from the others.
Anne, do you know what method the Chinese people are using at the minute? Is this the same one as the heat stuff we were talking about before?
As far as I know, the quantum satellite, as it's been referred to, basically beams down entanglement photon stays on the satellite and the other one gets beamed down to the ground, gets detected, and then there's some classical communication that takes place with the satellite, and traditional reconciliation and error correction, etc. And that's essentially how it works. At some point, I think that particular collaboration would be quite keen on a lot of people using those photons, because that beam covers quite a large area, and the satellite's not going anywhere for a while, so you might as well if you can. But I'm not entirely sure what protocols they have in place for use that.
So it's a lot.
Be able to detect the photons, which lack of ground station at the moment is also a problem.
Yeah, I think it might be fair to say as well that the satellite is potentially a point of failure in the communications chain, because it knows the other side of the value for how it's transmitted. So thinking about repeaters and sort of values in that space, where
True, but the advantage of using the satellite in free space is you don't need repeaters. If you're looking at the fiber optics infrastructure, that's one of the main problems and the main weak points for any kind of hacking is one of the, unless the Eve actually cuts the fiber and becomes itself on itself here, keeping it safe.
yeah,
But the advantage with the satellite is that you can introduce it just looks right there. The way
To be the practical applications guy, but surely shining a laser down from the satellite has exactly the same vulnerability of interception or something. I don't know if I'm missing something there, but I don't see why it being quantum entangled means you can't just capture that photon instead of
it does, but in that case, the legal parties don't have to do So if you put yourself in between the legal party, as in one legal party is the satellite, and the other legal party is the person who's supposed to get the photons on the ground. But if you intercept the photons, the person on the ground doesn't have that data.
so they can tell it's missing.
After that, you have some uncertainty principle that also means that it's unfeasible to detect and resend the same.
So it's a
And because
temporary.
you can detect and resend the same, you can't put yourself in the middle, detect, and then hope that.
So it's basically a seal as opposed to sort of encryption.
Cool. Yeah.
You mentioned using entanglement as a communications mechanism.
Mm-hmm.
Does that? I've heard this sort of in a sort of sci-fi context a lot in the kind of like faster than light communication. Does that information still obey the speed of light?
So in the entanglement sense, it is instantaneous. It's faster than speed of light. So speed of light kind of implies that there is something that's communicating between the two of those. In reality, it's just an inherent thing. Like they just know what is happening to the other.
So it's
Just
actually been proven that information that can actually travel faster than the speed of light in that context.
Technically, the difference is that you're looking at the state of something as opposed to two people having to communicate.
Yeah.
So let's say that Freya and I have a candle in the box each, and the state of my candle means that we know where the state of. If we open the box, you know what's in the other box. Entanglement doesn't violate special red because we know without having to talk to each other.
Right.
If information has to travel, that information can't travel faster than the speed of light. So I can't communicate to Freya faster than the speed of light.
Right,
But
the information's already been moved slower.
State.
Yeah, gotcha.
So detecting that state means that that's what Freya is going to have. But we haven't actually talked.
Right. That makes sense.
Yeah.
question regarding that. If you have two entangled particles and you're oscillating them at a fixed frequency, and then you start moving one of them at relativistic speeds.
Yeah.
So, how does that clock sync up with the time dilation that is involved if you have instantaneous communication?
I think at this point we're starting to move a little bit away from kind of what we're talking about in terms of quantum cryptography. For the benefit of everyone else in the room, so do you want 5?
Did I run through my bits and then you guys can, have more questions to put up to the panel, please?
Yeah, I think we do that. Shall we do 5 minutes so people can quickly go to loo and come back, or do you want to go straight into it?
I don't mind.
Right. Okay. All right. Okay. In that case, and if you wanted to chat to us in more detail at the end, yeah, just come and chat when we're done. I'm gonna grab some water.
Right, I need to log in. The wonderful bit where everything just stops working, because of course it would. But there's so many tech people around that there's no reason for me to be afraid of anything. Sorry, it's just the number one thing that happens at a conference. Shit goes wrong. It's like, regardless of how well prepared you are, you've been doing 2 talks, you're going to have a problem. That's not what I want. Let's see. There we go. Thank you. Where's my HDMI? Can you see it?
Yep.
It's at the back, isn't it? It's here. Is it F5? It's
F5's presentation mode, but if it's not detected, it sometimes takes like 30 seconds for it's going through about 4 boxes.
No.
Oh, there we go. So.
Oh, I see. It's quite slow then.
Yes, that's extended rather than mirrored.
Okay, so what do I need to do?
Somewhere within your.
See? This is why.
So, come out of and settings.
Thank you very much. This is the first time I'm using this one for presentation, so is it in utilities?
Possibly, yeah.
As soon as maybe it goes wrong. Utilities. That's not going to be it, is it?
It's not there.
I thought these things detected each other.
Yes, they usually. So it's just gone into a mode where it thinks that's a second monitor rather than a. You might be able to. You might be able to do it in the whatever your presentation was in. Is it just a document that probably not? So there is a set. If you go up to where that speaker is, there's sometimes an extra settings.
Sorry.
That's okay. It's still there.
It's still there.
Devices? Possibly. Let's try devices. There we go. So you
mirror?
Want to... Yes, mirror.
That's the one. Apply.
Sorry. I sort of nervously put this back in the box.
Just see whether or not it did. There we go.
Aha, fantastic. Thank you so much.
That bit plugs in.
Right. It plugs in.
That is your pointy, and that is your That's backwards. That's forwards. And then pointing.
Right. Hopefully I won't miss it.
I'm going to remove myself. Do you need to be plugged in?
If I do, then I'll plug myself.
Awesome.
Right. Should I start then? Yeah? Okay. So, as you can see everywhere, my name is Ghesquiere, but call me Anne because my last name is difficult. I currently work at the Experimental Quantum Information Group at the University of Leeds. This is my Twitter handle, but then again, my Twitter these days is mainly retweets of, nice pictures of cats or something. So, that's not. Basically, sure, augment my following and then boost my ego, but otherwise, it might not be worth bothering. Anyway, what I am going to talk to you about today. Current quantum computers. We are here because of that Google announcement. Well, I'm certainly here because of that Google announcement. So let's run through some quantum computers. Diffie criteria, because those are important for quantum computing, and you'll see why in a minute. Quantum algorithms. You've seen at least two, or you've heard of two. So let's go through that. Why not? Then I'm going to explain to you why encryption is going to die. At which point you should please let me run away first. I would like a 30-second head start to make it down the stairs. And then maybe post-quantum crypto, which not really, but sure, by this point somebody will have to make yourself feel better. Right, credit time references. I usually forget, or I don't get to my last slide or something, so I just thought I'd put it up now. You'll see a lot of very nice pictures. They are skin grabs. There you go. There is one who is not a screen grab, but I pilfered it off Wikipedia. And it's on Creative Commons or whatever license. Here's the way to find it. Nielsen and Schrank, that is so known as one of the Bibles that we have for anybody working in the field. It is also, at this point, almost painfully old. Nielsen and Schrank was written in 2001, if memory serves. Just so you know, the infrastructure behind Google and IBM and Rigetti is not in it. So have fun. However, it does have it does go through the physics, and it goes through algorithms pretty well. So it's a good text for at least those few chapters. Other references. So I did a Understanding Quantum Computing course online a couple of years ago just to have an idea of what's being said in the field, etc. If you find it running, it might be a good point. It's not very long and it's free, so might be one thing to look at. So here's why we are here. Google announcement, quantum supremacy and everything. Right? So here's their quantum computer, their 54 qubit chip quantum computer. So let's play a game. The game is known as Find the Chip. Right? Okay. Now, sorry, this thing is very confusing. I haven't actually gone anywhere beyond the picture, obviously, so I can only estimate via the picture. But I think, and it's this particularly bad picture, but this is why you should go to the New York Times and find a much better resolution one. The chip is here. It's a bit of not a great size squared, but it's square about this big, plugged in here. So what's all the rest then? This bit here, that is literally the outside of the fridge. The Google architecture and IBM and Rigetti, I think Microsoft as well, they are a bit of superconductor technology, right? Superconductor only works at very, very, very cold temperatures. We're talking within, I don't know, a degree of absolute zero, or as close to absolute zero as we can. It's very, very difficult to get to those temperatures, which is why you need what we call a cryostat. And this here, that is the outside of the cryostat. It's painted red because, sure, why not? You might as well have swanky colors. It is very heavy, hence why these things really, really, really thick. You have all sorts of vacuum pumps over there because it starts by creating a very, very high vacuum. You have all sorts of temperature controls here. Okay, so we have found the chip and we know what's on the outside. The rest of it here, these are cables for communications with your qubits. Sorry. It's like the last time I went driving. No one heard that. Anyway, so you need to, set your qubit. You need to be able to talk to your qubit. You need the qubit to do things, etc. So this is why all the cables here are for. Now, the idea here, it's pretty much the same thing, except that we're not seeing any of the outside, so there's none of the red bit here. But you can see at the top, the whole column goes up. And then you have, I think the chips are somewhere around here. And here again, you have all those cables for communication. Okay? Now, IBM, I don't know whether they were the first, but they were amongst the first to allow you to code on their system. Okay, so this is, you go through the IBM Quantum Experience, and you can actually code on those 5 qubits. Okay? So you can learn how to use all those gates that we saw earlier. Rigetti is the similar thing. So Rigetti has got 32 bits, or quantum bits, arranged this way. It also has a fridge, which I'm not showing because they didn't have it on their website. And it has also got a whole pile of languages and codes and everything that allow you to just code the quantum computer and simulate stuff on the quantum computer. Okay? Now, D-Wave is a little bit of a special case because the arrangement of the bit is different. D-Wave was one of the first, if not the first, to actually claim to have built a quantum computer. It's fantastic, and it was fantastic at the time, with a little caveat, which is that you need to be able to write the problem in a way that the D-Wave computer will understand. D-Wave solve problems using the annealing technique. That doesn't suit all computing problems out there. Okay, so the main problem with D-Wave is that you need to be able to write you need to be able to write your problem in the way that the computer will understand, essentially. I think at the moment it's got 2,000 qubits, so it claims to have 2,000 qubits. It has also got its own simulation environment, so you can log in. Well, you should register first anyway. You register, log in, input your problem, get your solution. Recently-ish, it has also come up with something that has 5,000 qubits. So this is their new next-gen chip. It's not just next-gen because it's 5,000 qubits. They've also bettered the way or increased the number of connectivity and connections that they have between their bits. So far, the previous, the 2,000 qubit non-Pegasus one has a qubit connected to 6 other qubits. This time they have each qubit connected to 15 other qubits. So they've got that much more processing power, so they can also deal with much larger problems. Yeah.
You mentioned the arrangement of qubits are different for different computers. How does that affect us? Why does that affect the different?
Connection between qubits means that you have some two-gate operations, as in, we'll see a two-gate operation in a few minutes. So the Pauli operation that Freya showed you is a 1 qubit, and it's 1 qubit because it only affects 1 bit. It flips that bit. That's all it does. But you have some operations that work on 2 qubits, where you have 1 qubit that controls the state of the other. You can also have some gates that work off 3 qubits, etc. But if you don't have connections in between those qubits, as in actual physical connection, then you can't apply those operations. So for instance, on the IBM, you do have some qubits where you're not allowed to put gates in simply because the infrastructure, those bits, those actual qubits are not physically connected. That means that you need to rearrange the order you're doing some operations in, which is why it's very nice to have a lot more qubits that are interconnected and connected with each other, because you have more freedom when it comes down to your code. Does that make sense? Right, you remember I told you that Google and Rigetti and IBM are superconducting qubits? These guys, IonQ, are building a computer based off ion trapping. So ion trapping is very good for building qubits because it keeps the qubit exactly where you want them. Okay, you can do a lot of really, really precise control with ion trapping. The problem of ion trapping is that it also requires lasers, it requires a big empty vacuum chamber. Like, the infrastructure itself is really non-trivial. I mean, you think Google is bad. Honestly, I don't know how these guys are doing it, but they are doing it, and they are doing it particularly well. And they've got single qubit gates on 79 qubits. They can pair up to 11 qubits together. So they do have they've also got really, really good fidelity, which means that they can distinguish states really well. Those guys, I think we're going to need to watch out for them as well. I won't go over the whole qubit thing because Freya went over the qubit and explained to you what the qubit is. Just again to repeat, classical bit is a 0 or 1. A quantum bit has a 0, the 1, and any combination of these. Okay, if you want to see it on the sphere, as we did earlier, the qubit, the 0 is the northern hemisphere, the 1 is the southern hemisphere, and then you're allowed everything else in between. And because you're allowed all of that extra space, you have a whole more, I'm sorry, the word is escaping me right now. So you have a whole more to play with, basically, and to encode information in, etc. So, obviously, the more qubits you have, the better. But you also want to make sure that they stay qubits long enough. Okay? There's one very big problem in quantum physics called decoherence, is when stuff stops being quantum and becomes classical. So decoherence means that this goes away, and all you're left with is these ones. Okay? Which brings me to the DiVincenzo criteria. I'm sorry, I must have left my diction at home when I got up this morning. These are the criteria that we need to make sure that we have a quantum computer and that have a quantum computer that works. So obviously, scalability with well-characterized qubits. You remember I told you about ion Q and ion trapping and the amount of resources it takes for just one? Well, that was why superconducting qubits were chosen at some point. It's because it was the fastest way to scale the infrastructure and to keep qubits well characterized. Now, characterized means that you can actually identify each qubit, which you need to do. Now, the ability to initialize states to a single fiducial state. That means that there's a point in your computation at which you need to make sure that all your qubits are at state 0. Right? Or, 001 or something. That is basically what this means. If you can't control your qubits and make sure that they all get to 0 at the same time or when you want them, it's a problem. Long decoherence time. You need to make sure your qubits remain qubits. Right? Otherwise, that defeats the whole purpose of having a quantum computer. It also influences memory. Okay? If you want to keep stuff in memory, you need to make sure that those qubits don't suddenly disappear. Because when they do, the information disappears with them. Universal quantum gates. I think this one is pretty self-explanatory. Yeah? Qubit-specific measuring capability. That means that you need to know what each qubit is at any one time. So these 5 here, that's for the quantum computer itself. Right? But the quantum computer needs somebody to input and output stuff at from. So these 2, they concern communication in and out. Okay? Communication in and out so that the stuff that you put in gets in there, and the stuff that gets in there you can take out as well. And then communication within. Okay? Those qubits have to be able to talk to each other. They are not in a vacuum. Well, yeah, they are, but you get the point, right? So, what are quantum algorithms? Who knows Shaw? Right, who knows Grover? Wow, you guys know some very, very smart people. I need your address books.
I know you.
I said smart. Anyway, so why do we have quantum algorithms? Well, you have a quantum infrastructure, you have a whole bunch of extra information. You really want to just limit it to classical algorithms. You want to use you want to use the qubits to their full potential, right? You want to use all of what quantum physics has to offer. And this is where the whole field of research about quantum algorithms come in. Okay? We're not just inventing stuff for the sake of it. Physicists, inherently, there is an amount of laziness about us that you can't deny. So, especially theoretical physicists, this is what mathematical approximations are all about, and yeah, go on. Disprove me. Anyway, so the 2 that are most interesting, useful when it comes to what's it called, quantum cryptography, all the field of encryption at large, is the quantum Fourier, any algorithm based on the quantum Fourier transform, one of which is Shaw, and the quantum search algorithm, the best known example of which is Grover. Okay? As something, you can also have a quick look at this. Stephen Jordan from Microsoft has started writing a comprehensive catalog of quantum algorithms. So if you want to have I invite you to go have a look. It is also depressing because it tells you that, there are some algorithms that are going to break Diffie Hellman. Hello. I did say I was going to scare you, right? So, quantum Fourier transform. Why do we bother ever with the Fourier transform? It's an integral, it's really painful, it takes a hard problem and it turns it into something that's easy to solve. Oh, that's why we like the Fourier transform. Except that the Fourier transform, the discrete Fourier transform classically, it also is very slow and very difficult to put into practice. So you have all sorts of algorithms in classical computing that are about making this faster. This is why the best known one is the fast Fourier transform, and everybody uses the fast Fourier transform because it was a genius piece of work. Quantum computation takes that problem and says, pish posh, I can do this so much quicker. You see why we have a slight bit of an issue with quantum computing? I mean, from the point of view of a physicist, it's brilliant. It means that instead of spending my whole career on one problem, I can just input it into a quantum computer and boom, solution. So, again, for the point of view of encryption, the one that really is a problem is the order-finding algorithm, which is short. Not exactly sure, it's built on order finding, and order finding works on phase estimation. So, do you remember your block sphere? You have the block sphere is the sphere that your qubit is on, right? So you have your qubit, which rests on the surface, but you want to know the angle that it's making, basically, and that's your phase. It's a bit rough, but it'll do. So, we want to know the vector that describes the state, because that's where our qubit is, which means that we need to know the angle that it's making, right? And this is known as the phase estimation problem. The angle, we call that the phase because we're physicists and we couldn't be bothered making it simple. So, single gate, okay? This one is known as the Hadamard. It does something, it always has to be there. It builds interference. And because it builds interference, it also means that you can take one qubit and then force it to do more things than if you just leave it on its own. This symbol here means that there's actually quite a lot of these, okay? Because they're all the same and they all do the same and they all interact the same with this one, I'm just running a single line. Simpler. Now, let's say I want to know what this one is. Where this one sits on the sphere. Okay? I'm going to take a whole bunch of qubits, cause them to be expand or something, and then I'm going to take a phase estimation protocol or phase estimation gate. Okay? And then that is going to act as a control qubit and force these ones into one particular state that I can then measure. Okay? IFT stands for inverse Fourier transform, and at the moment, it's a black box, because it's very complicated to know what's in it. It's I don't want to know what's in it right now. I mean, I could, one day, if, there isn't an actual inverse Fourier transform black box on IBM-Q, that would be too easy, so I'm gonna have, if I want to build it, but I've got 25 minutes left. I'm not going to go over the black box, okay? So, inverse Fourier transform, and then you measure. So, when you're doing the Fourier transform, you get a very good approximation of what your problem is going to be. Because again, you're taking a hard problem, and you're making it to something that's easy to solve. Yes, but you're making it something it's still a bit of an approximation. It's very, very, very close to what you want, but it's not an exact solution. Okay? So this here gives you a really good approximation of the angle that you're looking for. Not quite exactly, but really, really good. Generally, good enough that especially if you're trying to do this several times, you're going to get away with it. And that is phase estimation. Okay? Now, What about order finding? Order finding puts some number theory at the start, okay? And then all it does is that it takes some of these, it takes some of those, puts this here, x2 j mod n, here, measures, and then gets something which is quite close to what you're looking for. What you're looking for order finding is R. So you're getting something that is very close to S over R. Okay? And you have some number theory that you can then apply to actually get the value of R. Do you see why quantum computers can become a problem with order finding? Because it takes something that is difficult to do and then turn it into something that actually is not really.
Is that the integer discrete algorithm? Or is that not just completing the space? Have you tried?
Mark, help me here. I'm always mixing those two up. It might be. There is also a discrete logarithm way of coding short of finding all the findings, so not 100% sure here. Sorry, I've still run the algorithm only once, Mike. I haven't gone any faster. So factorization, it checks what the number's in at the start, applies order finding, does some more number theory at the end, and that's it. Right? That is Shor's algorithm in a nutshell.
Sorry, in the previous slide, just go back. Is the reason that you use the separate qubit that if you measured it directly, you would change the alternative principle would effectively change the result?
Yeah.
So you're basically using.
This is the one you want to identify.
Yeah. So you
use other control qubit.
Yeah. So you're using that to sort of infer what the value is without directly measuring it and then changing it.
Yeah. Right. Well, yeah, because this one interacts directly with the others.
Yeah. Okay.
So when we talk about Shor as being a quantum algorithm, there is a lot of classical into it. It's just that this bit here, the order finding, that's the bit that's actually really, really, really difficult, really, really long to do on a classical computer, and a quantum computer can do that very quickly. So, by RSA, well, yeah, and by Diffie-Hellman, with you have one of these that's called the discrete logarithm, Shor's algorithm, which basically breaks Diffie-Hellman or elliptic curves Diffie-Hellman. Fantastic! Are you guys scared yet? Well, no, you shouldn't be. Again, yes. This is the biggest number that's so far been factorized using Shor. Okay, we're not talking about 21 digits. 21, as in 7 times 3. That's it. So at the moment, we're safe. Yeah, safe-ish. That is why it's also a good idea to keep a lookout for some of the algorithms that come up, but I'll go through that in a minute, and also some of the new architecture. Grover is a fun one. So Grover, yeah, Mark?
Oh, sorry, I was just
Grover is going to start by flipping around the bit you're trying to find. And then it applies a transformation to everything. And it forms the answer this way. Now, Grover in itself does not look for the answer. It looks at where the answer can be. Okay, so it's not from a classical computing point of view, it's not looking at the value, it's looking at the pointer to that value. However, that's already quite nice to have, especially if, you're doing a sieve quantum finding thing to find your factors, and you find, it can also stop at where the first one is going to be. The problem I can see personally, this is my own opinion here, with Grover, and why I'm not finding it that super helpful at the moment, but again, that's my personal opinion, is because you do need to build, you need to have an idea of where that address is before you can flip it, which kind of isn't. So there are ways around this, but at the moment, I'm not finding that algorithm all that useful, specifically for that. Again, my own opinion. Budget. Yeah, that's a fun one. So, going back to this one. See that here? We're looking at, yeah, it's true. There is a point at which quantum computers are going to be, and they are fast advancing. I mean, what was it, 3 or 4 years ago, we had only like 19 qubits, and now we have 54. IonQ is actually like doing even better, and IonQ has got some memory as well, which should scare all of us. I mean, who wants to remember what we did the night before? But at the moment, a quantum computer is a giant money pit. It is investments in the millions. And when I mean millions, it's millions. It takes a whole team to run. Very specific set of skills required to run one of those. Which means that the likelihood of a hacker, the way I see a hacker, which is probably not right because those guys are like 9 to 5 and probably go to the office to work. It takes a lot of money to buy one. It takes a lot of money to house one. It takes a lot of money to turn one on, to run. I mean, looking at the electrical bill of Google should scare anybody. Seriously, I mean, we're not even talking environmental impact here, right? We're just talking about actual costs of infrastructure, the cost of the pumps, the cost of the electronics, yes.
Doesn't that make whoever is running a quantum computer a point of failure in cryptography wherever it gets applied?
Yeah, but that's called social engineering, and my understanding was that that is the point of failure for any cryptographic schemes, regardless of whether it's quantum or classical. I'm sorry, but honestly, I think the human element in any cryptography is like seriously, it's like the communication between. No, I understand your point exactly, but I think that the moment the what we have to save ourselves is that the people using the quantum computers are registered. At the moment, they have to register to go on IBMQ, to go on Leap, so there is some traceability here. They're also students. They are. I think IBM prefers when you have an institution email or when you're logging in through an institution because, so there is some amount of control. That being said, there is some information on how to break RSA using D-Wave.
Yeah, I mean, so my point was not getting someone to do it, but more that you're assuming that, that the only way to access these computers is through the registered system. If you can bypass the security to access the system, was my point. Yeah,
but again, there's a traceability element because I know for IBMQ, I don't know about Leap or Rigetti because I haven't used them, but the problems that you set up on IBMQ are actually logged. And you could run some simulations, but then again, you do take time as well of the whole system, and it's cloud based, so you have a whole sorts of extra data and metadata that comes in with your simulation. So you could set up some really big hacking things, but then again, there are also supercomputers that exist, and a lot of them. And if you can buy time on ARC2 in Leeds and write some short factorization and run that during your legal time, and they allow you to do it, then I'm not sure that you could, yeah, but there's a point where the research has to go on as well. I think at the moment what saves us is a traceability aspect into it, and that's why. Yeah.
I'm going to put on my tinfoil hat and ask about nation-state actors. Like, if there are a billion conspiracy theories online that, the NSA has just cracked into factorization, can do it in constant time or something. How much credibility do you think there is behind some of the sort of more grounded theories that nation-states might try and take over one of these things, or might have a powerful quantum computer of their own to do this, or do you think that's just completely outside the realms of possibility at the moment?
I don't think. At the moment, if they want to build themselves a quantum computer, the main problem is going to be the cost of materials. You're going to need to have the people running it. You need to have the infrastructure in place. You need to have the power to keep. You need to be able.
Nation-state actors will have.
Yeah, I mean, the NSA I'm sure if someone came up to the NSA and said, "Do you want to buy my quantum computer?" they would find the money.
Not to get paranoid, but you're also assuming that it hasn't already. There's a point here where, you can only deal with the enemy that you can see. It's the devil, at this point. We know where some of those big computers are. Mainly because the guys running those computers have been very, very forthcoming into saying, "Look at our shiny machine!" Right? But, I mean, Microsoft is doing research on it. IonQ is doing research on it. Google was doing research on it for years. Absolute yonks, we didn't hear about it. We knew there was something going on, but we didn't know exactly how much and how many, etc. I mean, D-Wave have been on the market for since 2007, which might be wrong, and now they're pulling out a 5,000 qubit, and that's already 2 or 3 iterations in. Well, there's a point at which, there's only so much that we can do. Which is why we get here, right? I mean, at the end of the day, there's nothing preventing us from somebody malicious logging into IBMQ or logging into the Leap or anywhere and just deciding, you know what, I'm going to start running this code and break RSA. Fun. So what happens then? Well, what happens is that we continue to do some research into quantum key distribution, because the key is also one of the weaker parts of the encryption. So if we can make sure that key is unhackable, then we've already one step closer. And post-quantum crypto is, I think, a very, very underrated area of research. People in Royal Holloway are very keen to tell you that there are at least 2 or 3 codes that somehow came up in the 60s and that none of us know about, and are actually unhackable on a computer or otherwise. So post-quantum crypto is going to be the one place where everybody should look. Especially because, at the moment, there's also something that all of that layer of encryption that can potentially be broken, it would be good to either renew the encryption or add a layer of encryption onto it. And what you can do is add a layer of post-quantum crypto to it, which is a minimum effort, if you will, because it doesn't actually force you to do anything to the encryption that's already in place. It's just, adding another layer to it, so that you can be sure that even if a quantum computer or somebody has used a quantum computer and just broken RSA, or Diffie Hellman or AES or, all of any of those schemes, then you have a layer that they just can't break into. And post-quantum is inherently classical. It is pure maths, as in pure maths, but it's also very underrated. I think somebody ought to give those guys in Royal Holloway a shootout so that, some of those actually make it outside of Royal Holloway. But they did, I think, submit stuff to NIST. So there might be a few schemes that are currently being reviewed under the NIST PQC competition thing. Right, that's me. Thanks for listening. Sorry I took the piss. Yes.
I had a question from some of the slides though. I've never heard the terms stationary and flying qubits. Can you define what that means in a qubit? What is a stationary qubit and what is a flying qubit?
A stationary qubit is one that is stable. The way you define stationary in physics is that it's basically at equilibrium. So it's a something that isn't evolving. And a flying qubit in that respect is something that is evolving. So you need to be able to pass information on from flying qubit to. I'm seeing it as a RAM versus ROM kind of interaction, but maybe that's wrong. Yes.
You mentioned with the post-quantum algorithm stuff that there's a number of different approaches that are being considered. How much stock do you put in, for example, lattice cryptography as a solution for it?
The way I heard it is that lattice cryptography at the moment is quantum secure. What I mean is that it's secure against quantum attacks. Oh, by the way, one point that I should probably have mentioned is this one. At the moment, that's the biggest threat. It's the next big quantum algorithm. At the moment, we know we can defend against the one that we have, which is why we're trying to defend against Shaw, by basically increasing the length or something. But some other genius could come up with something else entirely. Yeah.
With classical computing, we have obviously the Turing machine model to work out roughly how difficult a problem is, at least how hard it could possibly be. Do we have a similar thing for quantum computers that we can use to investigate how hard these things are, sort of limit the power of these algorithms?
Honestly, that is completely outside of my realm of expertise. I couldn't tell you. I don't know enough complexity theory or anything to even begin giving you an answer. I'm really sorry.
Based on both the topics, I get a feeling that infrastructure is what is holding us back. Do you reckon if the infrastructure problem is solved, then this can definitely become a practical solution? Is the theory behind it sound enough? But if the infrastructure problem is solved, then it's a practical implementation.
At the moment, the way I see it is that there are at the moment, I think the technology is holding quantum computing. The technology of quantum computing is holding its danger back. Yeah, the theory is sound. That being said, that's also where post-quantum comes in, and why I think post-quantum should take a bigger spot under the sun, basically, because there's only so long the technology is going to hold back, basically. So yeah.
On that note, so in terms of increasing reliability, increasing fidelity.
Yeah.
One of the methods with the architecture is centered around topological models. Is that anything of promise, or is it just it's transcended the problem of fidelity and reliability to finding some particles that you don't know how to construct?
Right. Topological quantum computation breaks my brain, literally. Like, it takes my brain and puts it through, I don't know, a blender, and then hands me some mush that I'm supposed to make sense out of at the end. So honestly, it's the same. I don't know enough about topological to give you an answer about this. And like, there are a lot of really smart people that will probably like be able to give you an answer, and a simple answer. I'm not one of them. Sorry. Like, again, topology is. I understand what a torus is, but that's about as far as I go. Yeah.
You briefly mentioned quantum key distribution, and one of the points that is often made about that is you can't eavesdrop on it because this would not get to the receiver because you'd have to intercept it. You couldn't retransmit it.
Yeah.
And I remember when I was last looking into it, the main problem was, like, theoretically it's great. You would send a single photon, they would get a single photon, it would all be great. But you have to account for losses in the system, and at the time they were having a problem where they basically had to accept that only 5% might ever get to the receiver, so they'd had to go, like, as long as we've got 5% of what we send, then we think we've got it, which leaves room for an eavesdropper to get into that system, because, you know, they could take any of the other 95% of photons that were sent, and you wouldn't know that they were there. Because, and is that something they're still moving towards? Are they still looking at getting down to the single photon, or like is that something we're looking at, or is it, you know, we've given up on that and we're going for a different method?
Oh no, they're looking into improving that. They are always looking at improving their system and improving the fidelity and improving all of the steps in between, especially when you come to repeaters and having nodes. And all of that is the quantum part. There's also a lot of research being done in the classical bit. All the reconciliation and error correction and privacy amplification is a big one as well, where as long as you have two legal parties that can talk to each other, even if anybody can hear, but no one can change the information being passed in between. If they start with a large enough data set, they can build a key a certain way. So there is research being done both into the production and passage of the signal or transmission, and there's the whole error correction and reconciliation and privacy amplification on top of that. So quantum key distribution really has 2 bits in it, and you can't do without the classical bit in that. Yeah.
Surely, I don't understand the information content of qubits at all, but surely you could just tag it as, you know, this is qubit number 1, this is qubit number 2, and then you say which one you received back. Because if someone intercepted it, you wouldn't be able to read that qubit, and so you could say, I didn't get it from me.
True. Now the problem is there are several aspects to this. The first thing is that it is very, very difficult to send a photon. As in, it is technologically, it is humongously difficult to send just one photon. But if you could send photon 1, photon 2, photon 3, etc., you have to deal with what gets lost in the fiber, because an optics fiber has got a lot of loss in it, especially if it's a single photon traveling. So somebody could expect 1, 2, 3 photons, and then 2 is missing, for instance. So they expect 1, 2, and 3 because the detector is supposed to click at clock times. You have times where the detector clicks when there's nothing there. Because detectors are not necessarily perfect either. So that's also why it's very difficult to just send one photon, then another one, then another one. Simply because it's just, light is, very, very difficult to...
If one of your packets, I think this is a network thing, if one of your packets get through, you send off 100 different packets of different keys, and you get one of them the other side, you can just agree to use that one over a classical channel. You can just say, I got your letter number 23, let's use what's inside that as our key.
Yes, but if somehow the eavesdropper has gotten some information about packet number 23 and enough information about packet number 23 that if you just say, let's use the 100 bits that's in packet number 23, the eavesdropper could have 15 bits out of those. Do you want the eavesdropper to have any bits out of those? The problem is that that's why you need the classical information, the classical communication after that.
You say you send the quantum.
So you'd send like 100 of those packets, and then you encode which packet you agree on some form of secret code to take those packets without having to disclose which packet.
So you're talking about the qubits. I was sort of using the analogy, but if you send a qubit, the problem is they're getting lost on transit. You can't tell it's being read and it being lost. So surely, if you just if you send lots of different ones and go for the one that has got to the other side intact, then you know it hasn't been lost already. You just agree to use that.
Oh yeah, but that's usually the way it ends up happening anyway. Also, if Eldar for instance, you could have everything else as a 0 and this one being the 1. So you have the sequences of 0 and then 1 in between.
But that means that missing out an error rate doesn't really matter. It just takes slightly longer to agree on kit.
The problem is if your error rate is too large, then there are other bits of classical computation that it's not worth doing because you don't decrease the amount of errors. There's a point where if you have, let's say if you have 25% errors, no matter how many times you run your error correction, you are going to end up with 20% errors. Counting 5% that disappear. And by the way, I am completely inventing those numbers, so don't hold me to that. The point is that you can start with a certain amount of errors, and that's fine because there's noise, there's pollution, there's loss, there's God knows what, that counts, and etc. If you want to get really technical about it. So lots of things that happen. Except that, if the number of errors is too large, then it's not worth your time. Simply because it won't reduce no matter how much effort you put into it. And if you can't reduce the errors no matter how much effort you put in, I don't know, tighten the screw and try it again. Yes?
You speak to any of the work that's happened, I think it's the University of New South Wales on quantum processing in silicon sort of developments. So some quite very interesting research coming out of that part of the world.
I must admit I'm not familiar with that. So the answer to your question is no, I couldn't comment. Simply because I haven't kept a lookout close enough to it. But yeah.
It's I believe they more or less tried outsourced it, so they privatized the research around it. Sorry, an ex-housemate of mine happens to be a researcher there, and it's and they have. I don't know of any cryptography work being worked. They're more in how they embedded the chips as far as I can tell, it's 3 professors with 3 different methods, and they're trying to collaborate because they're getting some high precision. And I've heard that they can have basically introducing single atom defects into the silicon crystal to make atomic level. Transistors or whatever you would call it fixing a qubit in.
Yeah, it is one of the again, quantum superconductors and ion trapping are 2 of the ways that people have created qubits, but they are not the only ways people have created qubits, and there is research being done in missing atoms in diamonds, for instance, and quantum dots, and you can get some really, really high precision qubits if that is the particular research. my worry about it is that it's not just the chip itself that you have to consider. Looking at the DiFincenzo, you need to be able to make a machine. Like, you need to have the rest of it, and sometimes the rest of it takes a lot of space, and sometimes that's basically how the scalability aspect of it is going to work out. So it can be that there is a lot of research being done in the NV science centers in Diamond and all quantum dots and etc. That might be relating to the ones in New South Wales. Again, I'm not entirely sure. But at the moment, the two architectures that have been the most successful certainly is the superconducting one, because I think it's the one where they found it easiest to just cram as many qubits as they can, very, very small amount of space. But yeah, research is still being done because it is still expensive it's like the extra.
The cohesion increase the times and the stakeholder.
Decoherence. Yeah, decoherence is it's one of the major pitfalls. If you want to, entanglement dies very quickly, but qubits tend to decohere very quickly as well if they are left in the wrong environment, to put it bluntly. That's why superconducting has to only happens when it's very, very cold. That's why ion trapping works, on a very specific set of conditions, because you can't trap ion at room temperature. Yep. You had a question? Oh, I thought you had a question.
You mentioned, I think both of you mentioned that a lot of quantum cryptography is reducing the step count rather than necessarily reducing how long each step takes.
It is and it isn't. Yes, you go ahead with your question. Sorry.
I was just going to ask what sort of timescale are we talking about for the actual measurements and the individual steps in
Depends what kind of computer you're using.
Honestly,
order of magnitude is, or within 5 orders of magnitude, it's fine, probably.
Again, I think it depends specifically on the computer you're using, the algorithm you're trying to use. Do you include all of the time it takes to set up, or do you literally just include the time it takes to do the operations? Because to do the operations, it's kind of no time at all. But if you've got 10 different lasers that you want to set up and things like that, should take weeks.
Yeah, I mean the quantum. Just to get to ultra high vacuum, it takes. It takes a while to get to ultra high vacuum. Just that. Then you have to set up the stuff properly. There's all that quantum there's the classical coding that you have to do before to make sure that you have all of your qubits initialized the proper way. So I think the quantum bit itself, the advantage is that it goes much faster and you can drastically reduce the amount of operations that you have to do. So you could be talking about, I don't know, a day of computation if it comes to the AHA core. And I'm hoping for a day of, honestly, I couldn't. But
each operational step, are we still talking like nanoseconds, picoseconds kind of thing?
Well, that's why you need to, you'd have to go quite fast to beat decoherence.
Right.
And that's why you need long decoherence time. Decoherence can happen in the nanoscale, nanosecond. Decoherence and entanglement sudden death are two events that happen extremely quickly. So if you can control this and make it a qubit that live for seconds to minutes, then the way I see it is quite simply this is how long you have to run your code. If your code can't run past that, it is going to outlive your qubits, and if it outlives your qubits, you don't have the answer at the end. So you need a code that basically can run within the lifetime of your qubits.
The actual length of time it takes to, do the transformations and run the different gates in the quantum system isn't necessarily that long at all, but it needs to exist long enough for you to be able to measure it. Some of these things are probabilistic measurements, so you need to measure for quite a long time to see when, it's most probably going to fall, rather than it just being like counting to a single photon. It's like, okay, we need a few of these to see what the probability structure looks like. It's not a clear, exact answer like you might want. It's like different things take different lengths of time, and it depends what you're doing it on. And that kind of thing. I mean, the amount of time it would take to perform a powder gate or Hadamard gate on some lasers. The actual act of doing that itself is nothing at all, but all the stuff around it is the stuff that takes time.
Well, yeah, I mean, getting measurement of a laser itself, you can shine the laser at a photodiode and, read the light, and it takes hours just to get the laser to point in one direction. It is, for having done it, it is surprising the amount of time that it takes to make sure that your laser is going to point exactly where you want it. And you're thinking, it's like it's a dot, it's not moving.
Yeah, I am very familiar with the annoyance of lasers.
Yeah, but that's why, also why people have moved towards superconducting. But then you do have other issues with superconductance, and you could have if you have a dud that Sycamore paper in Nature was published with one dead qubit in it. It literally is. There's a dead qubit in it. And they admitted there's one of their qubit that didn't work or something. Which, that's whatever, it's fine. They build it, it's like you have some microprocessors or that come in with defects in it, and sometimes you don't control exactly what comes out, which is why lasers are nice, because laser can be readjusted, etc. But I mean, at it's all about checks and balances at this point. You have to balance the cost of manufacturing, the cost of stuff, and then if you have to, make a new chip every 6 months because some amount of computation just deadens the old one, then that's basically how long you have to run your computation.
And then becomes an ongoing cost as well.
Hence why I'm not seeing I'm not seeing hackers using quantum computers anytime soon. That being said, there is nothing preventing anybody from using one of those IBM Q, and actually there is code on Leap to simulate something that is going to break Shore eventually. So I think people should keep an eye out for that. But unfortunately, it works with everything. It's the same with supercomputers. If you have anybody using a supercomputer in a malicious way that finds a way to break some encryption or some, hacking and manages to put it onto the radar or something, then there's very little you can do.
Yeah, it's a tool that anybody can use for what?
At the end of the day, yeah, it's a tool. It's like Dan was saying this morning with all the codes that gets, it's a whole idea about the proof of concept and finding the bugs and publishing the bugs and publishing the, all of that. It cuts both ways at this point.
Because you mentioned the different ways in which they make quantum computers.
Yeah.
Are the computational properties of the qubits the same across the different ways of which they're made?
There should be, yeah. A qubit should react the same way, regardless of the infrastructure that it's in. D-wave is slightly different, not necessarily because the way the qubits are connected, because the way qubits talk to each other. But a qubit is supposed to be a quantum bit, the same way as a classical bit is the same bit in, a Mac or Windows or a Dell or anything.
I guess my question is possibly more Mexican, because you say there's a difference in what was a D-wave, how they are connected. So like are the different quantum computers, do they exhibit the same properties? In the sort of asymptotic bounds on algorithmic complexity.
Ooh, there's a lot to unpack in there.
So
the DiFincenzo, when it talks about universal quantum gates, is that the quantum gates have to be a Hadamard gate or a bit flip gate is supposed to do the same thing regardless of the infrastructure that it's in.
Yeah.
So the gate itself shouldn't change. It's been argued that D-Wave is not a universal quantum computer because, again, you need to be able to write the code in a way that that computer can understand it.
Yeah.
And that is basically all I can say about your question because I'm not entirely sure I know enough for the rest of it. My field is not entirely quantum computing. I'm more quantum key distribution. I'm close enough. I understand quantum computing, and apparently I can talk for a long time about it as well, which is a big surprise. I wasn't expecting to be talking at this time of day, but never mind. Yay! On this good words, I'm going to go and have a coffee.
Okay, thank you.